Another situation in which simple harmonic motion occurs is in an alternating current generator. Alternating current is produced when an armature, which is like a piece of metal between the poles of a magnet, rotates about its axis in a magnetic field. This armature then creates current. There's a formula that we can use to talk about the voltage generated by this situation. It's E of t is equal to E sub 0 cosine of omega t, where E of 0 is the maximum voltage produced, and omega over 2 pi is the number of revolutions per second of the armature, which is the frequency. So notice if you flip it, it's the period. So let's do a problem involving this. It says ordinary 110 volt household alternating current varies from positive to negative 155 volts with a frequency of 60 hertz. Hertz is the unit of frequency. Find an equation that describes this variation in voltage. So the problem we start off with when we're writing this equation is, do we start with positive or negative amplitude? Well, for this particular case, because we really don't know, we're actually just going to assume that at time t equals 0, that we're going to start at positive 155 volts. So E of t is going to equal 155 cosine of something t. To figure out what omega is, they gave us omega over 2 pi. Remember that that's really just frequency. So we're going to set omega over 2 pi equal to 60. However, if for some strange reason you really feel like you need to change this to be in terms of period, you can also do 2 pi over omega is equal to 1 over 60, because if the frequency is 60, the period is 1 over 60. You'll notice that both equations are the exact same thing. Cross multiply, I'm going to find out that omega is 120 pi. So the equation that best represents this situation is E of t is equal to 155 cosine of 120 pi t. In an earlier assignment in one of the sections, we ran across something called damped harmonic motion. We didn't call it that at the time, but we gave you this way of graphing something in the equation where the amplitude of a sine or cosine curve changed over time. This tends to happen when we actually deal with friction. Remember the case of the oscillating spring? We pretended like the spring was in a frictionless motion, but you know from your lessons in physics that over time that spring eventually is going to stop. It doesn't actually continue its motion of up and down at the same amplitude forever. So we have equations to deal with damped harmonic motion. The equations are y equals k e raised to the negative ct sine of omega t, or same with cosine. C is called the dampening constant. It's greater than 0. K is going to be the initial amplitude of the motion. Remember, we call this damped harmonic motion because the amplitude is going to decrease over time. And 2 pi over omega is our period. However, a lot of times they don't call this the period. They call this the quasi-period. And that's because we know that in a surface with friction, that the period, there's really no period, I guess we should say, because the motion doesn't start and stop at the same location over a certain period of time. This was a graph of what damped harmonic motion looked like. And again, hopefully you should remember that we've done this in class. We ran across a problem, or it was a homework problem, it was an in-class problem, I can't remember which, but we had done this before. So problem 7. Two mass spring systems are experiencing damped harmonic motion, both at 0.5 cycles per second, and both will have an initial maximum displacement of 10 centimeters. The first has a dampening constant of 0.5, and the second has a dampening constant of 0.1. First, we're going to find the functions of the form g of t is equal to k e raised to the negative ct cosine omega t to model the motion in each case. So let's start with the fact that the very beginning of the problem told us that both of these systems have a frequency of 0.5 cycles per second. So I'm going to use that to find my omega value. So it doesn't matter which one I use. If I want to use omega over 2 pi is equal to the frequency, that works. So when I multiply, I'm going to find out that omega is 1 pi. They also told me that both have an initial maximum displacement of 10 centimeters. Remember, we said in a dampening harmonic motion circumstance, there's this initial amplitude, and you know over time that amplitude's going to change. So we're going to start with k is 10. The second part of the problem then says that the first dampening coefficient is 0.5. Sorry, the first one is 0.5, the second one is 0.1. So those are my c values in each equation. So one of the equations is going to be g of t is equal to 10 e to the negative 0.5 t cosine of pi t. And the other equation is going to be g of t is equal to 10 e raised to the negative 0.1 t cosine of pi t. Now that we have these two equations, in part B we're going to look at the graph of each equation and determine how they differ. In order to graph the first one, I need to make a viewing window on my calculator that's appropriate for this circumstance. Now, remember we said, so I'll call this, just call it first equation. For the first equation, the initial maximum displacement was 10 centimeters. So I'm going to make my upper and lower values just a little bit more than that. So maybe I'll make my y minimum negative 12 and my y maximum positive 12. The second part was that my my frequency, was 0.5, which means that my period is 2. But if I only look at one cycle of this, I'm not really going to see what's going on. So maybe I want to see a little bit further. So I'm going to start at x is 0, and I'm going to go out to 15, just to pick a nice number. I mean, I could pick 10, 15. It really doesn't matter. So here's what your first graph looks like, and you can see it here at the beginning where it starts at this high value, and then it just kind of goes down from there. If I leave the conditions in my calculator the same and graph the second equation, the one where the dampening coefficient was 0.1, then this is what my graph looks like. How do they differ? Well, I want you to notice that the first graph kind of fizzled out much faster than the second graph. So lowering the dampening constant made it dampen slower, which is really what happened here. So because this example shows that the larger the damping constant, the quicker the oscillation dies down, we have some other examples of where this occurs. When a guitar string is plucked and then allowed to vibrate freely, a point on that string will undergo damped harmonic motion. We kind of hear that dampening motion as the sound produced by the vibration of the string fades. How fast the damping of the string occurs is kind of a property of the size of the string, the material it's made of. Another example of damped harmonic motion is the motion of a shock absorber on a car. When you hit a bump in the road, the shock absorber is engineered to damp the motion as quickly as possible. That means it's got a really large C, and to have as small a frequency as possible. But if you think about the example of the tuba player, The tuba player's note is not a damped harmonic motion because the note can continue as long as the player can maintain the loudness of the note. As long as he can breathe into the tuba, he can sustain the note. Electromagnetic waves that produce light also not damped harmonic motion. They're really just simple harmonic motion. So let's talk about a vibrating violin string. The G string on a violin is pulled a distance of 0.5 centimeters above its rest position, then released and allowed to vibrate. The damping constant C for this string is determined to be 1.4. Suppose the note produced is a pure G whose frequency is 200 Hertz. Find an equation that describes the motion of the point at which the string was plucked. So let's go through the problem. This being pulled 0.5 centimeters above its rest position, that's my initial amplitude, that's my K. They told me the damping constant is 1.4, so that's my C. And since I know the frequency is 200 Hertz, that means that the period is 1 over 200, so I'll solve this equation in order to find out what omega is, and it's going to be 400 pi. So the equation is going to be y equals f of t equals g of t equals, k was 0.5, e raised to the negative 1.4t. Here's a fun question. Should we use sine or cosine? Well, because the string was pulled before it was released into motion, as opposed to just magically starting its motion from equilibrium, we're going to use cosine, and then I'll put in my 400 pi t. And that's the equation that represents the motion of that string on the violin. In example 9, a stone is dropped in a calm lake, causing waves to form. The up and down motion of a point on the surface of the water is modeled by damped harmonic motion. At some time, the amplitude of the wave is measured, and 20 seconds later, it is found that the amplitude has dropped to 1/10 of this value. Find the dampening constant C. All right, so since we're only talking about the amplitude, because the amplitude is governed by K e raised to the negative CT, we're going to use this and create an equation to find out what C is. So this is my initial amplitude, and then I have an amplitude 20 seconds later. That's going to be written as KE to the negative CT plus 20. If these are equal to each other, when they're equal to each other, we said that the first one is, it's the new amplitude, the 120 seconds later, has to be 1/10 of the original one. So now I have this equation that I can solve for C. And you may be looking at it going, well, there's a lot of stuff going on in this equation. And that's okay. This is what's going to happen. First of all, because both sides of the equation have K, they're going to go away. The second thing I'm going to do is I'm going to use the property of exponents, one that you've used many times but you forget about. I'm going to rewrite this as e to the negative CT plus negative 20C. And what a lot of people forget is that when you have an exponential term and the exponents are being added, they can be rewritten as the product of these two. We don't usually go that direction when simplifying expressions. Well, now I want you to notice that both sides of the equation have an e raised to the negative CT. So now I'm left with 1/10 is equal to e to the negative 20C. We know how to solve this equation. We have to get c out of the exponent, so we're going to have to use the inverse operation of e, which is ln. So we're going to do the natural log of 1/10 is equal to the natural log of e to the negative 20c. Remember, these cancel. So the natural log of 1/10 is equal to negative 20c. And then we're going to divide that answer by negative 20. And the natural log of 1/10 divided by -20 is approximately 0.12. So my damping constant is about 0.12.